Well, let us start today's lecture. Basically, what I wanted to start today is really talking about inelastic behavior. So up to now, we studied different models of elastic behavior, either linear elasticity or nonlinear elasticity. And we have seen that in the linear elasticity, the end result is by using the finite element method solution, you actually have a set of the linear algebraic equation that you learn how to solve and recover all the fields that are of interest to us, that is displacement, strain, and stresses, and so on. Now, in nonlinear elasticity, you need a little bit more in the sense that there's an idea of incremental analysis that allows to simplify nonlinear elasticity problem to a succession of a linear elasticity problem, which are approximation to the real behavior, and then eventually use iterative Newton's procedure or any other iteration to really obtain the even better solution than what incremental analysis can deliver to you. So all these things are useful for nonlinear analysis when inelastic or static behavior, but we need something more. Well, it turns out if you really want to have a little bit more comprehensive behavior description, in particular, what really kind of characterizes the inelastic behavior is the notion of dissipation. In other words, in the elastic behavior, all the work of the external forces eventually can be used to store this into the internal energy of the material. And once these forces are removed, the internal energy is kind of released. And basically, the material comes back to its original position without any damage, without any change of the, let's say, properties that you had initially before the loading was applied. So in the elasticity, theoretically, you can do this infinite number of times and everything's fine. Yet we know from first structure that you study, which is your body, that that happens not to be the case, because every day you might have a little bit of some kind of problem, and then basically that problem accumulates. Even if you have not been through really like extreme event, the accumulation of these things would lead to eventually some kind of damage and a dissipation of your energy in whatever you want. So any solid material, any solid body, a structural system behaves in this manner. In order to be really fully able to define this dissipation, the proper framework of that is really thermodynamics. So what is the thermodynamics? So the thermodynamics is the basically mechanics with the rate effects, that would be dynamics. And then on top of that, you put a heat transfer type of phenomena, that is, you account for the temperature. Well, in many materials, the behavior does depend on the temperature. But if you really kind of, for example, if you take metals to be on a very, very high temperature, then the yield stress of metals goes down. For example, for some other material like natural clay that is used for masonry, if you kind of heat it to a very large temperature, then it goes up. But after 800 degrees, it goes down, because this is the temperature that was used to produce it. So really, temperature itself is important, plays an important role in the behavior of the material, in defining properties and other type of things. But here we really mostly use it in order to kind of put a proper framework for the inelastic behavior. And in particular, for that, in order to complete the full picture, the more thing that we need is so-called internal variables. I'll talk about that in a moment. These are something like a plastic strain, let's say damage compliance, hardening variables, and so on and so forth. Then I will take a plasticity to start with and show you in 1D problem, we go back to the first lecture, how you actually carry out computation when you have plasticity. So difference to elasticity, either linear or nonlinear elasticity, that you actually have to take a very precise definition of your loading program in order to define what exactly would be the final state. Namely, it is not the same if you're simply loading in one shot or if you're doing several cycles of loading and unloading. Even though that you find yourself with the same stress state at the end, with some kind of situation of this kind, basically you will definitely not have the same plastic deformation which gets accumulated, because several cycles of loading and unloading could certainly lead to much higher plastic deformation. Then this is explained for 1D case, and I'll show you then the kind of first plasticity model, which had really very large success because it was very typical of metals. This is so-called von Mises criteria. That's a generalization of Tresca criteria. And basically, I show you that even though it is 3D model, it has only one mechanism, which is basically related to the shear deformation, or which could be very nicely expressed with the deviatory part of the stress. And so you only have this mechanism triggering, so it comes down to be like a really one mechanism. And if you put it in the right, let's say, a representation, which is deviatory plane, that it happens to be, again, sort of one-dimensional problem. It has something called radial return mapping and so on and so forth. So it's very robust on top of being the first one, which is useful. But nowadays, there are many composite materials, and von Mises plasticity is by far not the only one that is of interest to the application. So you can imagine presenting now a catalog of different plasticity criteria, which will be the most appropriate for different composite materials. Or the way I took it, I actually took von Mises, and then I put all different refinements, what I call the plasticity model. What these refinements are, this is basically enhancements that you might add in order to increase the predictive abilities of your model. So you can have like a not only linear hardening, you can have a saturation, that means non-linear hardening. You can have something like a kinematic hardening that you can take into account a cyclic response. Then you can have something like a ray dependence response that would be viscoplasticity. You can have a nonlinear, let's say, elastic response plus plasticity. Then you can have multi-surface criteria, and many of them are taken like you have a Tresca, you have a Rankine, and so on and so forth. So once we defined everything about plasticity, I'll show you there's an alternative to that. There's something called damage model, and that model is there to take into account change of the elastic properties. And basically, rather than taking irreversible plastic deformation as internal variable, this one takes something called damage compliance. Damage compliance is sort of, to start with, inverse of the elastic modulus in 1D case, and then can go bigger and bigger as more as you get these cracks. And then what we managed to do is kind of contrary to many other early works on damage in the style of Kachanov, especially typical of French school, with Jean Lemaitre and collaborators. We managed to put this image into the same format as plasticity, and that certainly simplified the fact that you can couple plasticity and damage and produce in a single shot something which is really the most useful for cyclic loading and predicting type of, let's say, a failure under cyclic loading. It could be fatigue, it could be earthquake, it could be something, whatever you want. And so we follow this, and hopefully you'll find in the process your favorite plasticity or damage criteria, and if not, you'll be able to build it yourself and know how to do it. So the main novelty from what we had is the fact that we are now turning to thermodynamics. In other words, we are not only studying mechanics, but we also study heat transfer. Some of the books I cited here are early references. As I said, Trussell and Knoll was the first comprehensive attempt to put the thermodynamics. And basically, really what they've done correctly was a thermoelasticity. If you go to thermo-inelasticity, basically, they were advocating, beside these curvilinear coordinates that made really reading quite difficult, they also advocated materials historical log memory, which is if you want to get stress at time t, you have to integrate behavior from minus infinity to time t. First of all, who knows what happens at minus infinity? Nobody was there anymore, but to tell you what it was like at minus infinity. And secondly, it's not really practical because such a log integration is not the way to go. So it turned out that the proper way is really this internal variables, which I described not by integral equation, but by differential equation or evolution equation. Other books which are also of interest, which are maybe more readable, a book of Ziegler, who was professor in Zurich, this Swiss Federal Institute of Technology in Zurich, and Ericsson, really my favorite because he used this notion of tweaking a 1D model. So I get back to 1D model following sort of Ericsson approach. So basically took a bar and basically said that you have again, like a pen, and you put in gravity field, and on top of that, you put it in a, let's say, uniform heating environment. And then basically you can cut the cross section of this bar and realize that stress in each and every point of this cross sections happen to be the same. So you can devise one-dimensional model, that is, you're taking a single fiber or you take a cross section A to be equal to 1. And then this time around, we already went through 2D, 3D version. We know that given the proper choice of the coordinate system, putting x-axis along axis of this pen, you will have only one non-zero component, which is called sigma. and all the other stress components are equal to 0. And then in terms of strain, given that you might have a reasonable Poisson's ratio, you'll have again one strain component because the elongation would be epsilon, but the transverse direction would be minus nu times epsilon. So as soon as you know epsilon and you know nu, you can compute the other two. So again, you end up having only one component of stress, one component of strain, one component of displacement. But this time around, you need some more. You'll need one, let's say, a temperature. You'll need also entropy. You need a heat flux, and so on and so forth. So first of all, if you really want to study thermodynamics, you have to define a little bit more, let's say, loads, a little bit more property. Geometry is the same. You have the length of the bar, and you have a cross section. Here we take it equal to 1. Now, the loading could be distributed loading B, of course, imposed displacement and imposed traction. And this time we add also a heat source. Imagine if you have like a heating which is put in the floor of your room. So you have a heat source everywhere in the floor of your room. Many apartments are built this way, so you don't have this heater which is taking place in your, let's say, room or whatever it is. So basically, you have to define this loading not only in terms of this heat source, but also of the imposed temperature somewhere on the boundary and the imposed component of the heat flux. Now, if you want to define finally the behavior of the material, make it the simplest linear elastic. For mechanics, we saw that you need Young's modulus in 1D. Well, if you need 2D, 3D, of course, you need also Poisson's ratio. And for the heat transfer, you need something called coefficient of conductivity. So coefficient of conductivity is a measure how good material behaves in conducting heat inside. So basically, right now, there's a big push in Cadarache, in the south of France. They're trying to come up with a new technology where the nuclear reactor that is used nowadays will be just a starter. So basically reproducing a fusion, which is the type of reaction that takes place at the sun, in order to provide a new generation of energy. And so one of the key challenges is providing the material, which has been very perfect heat conductor, to be able to handle such a really, let's say, conduction of heat at a very high temperature, which is a really huge challenge, because if you just perturb it a little bit, everything goes and explodes and so on and so forth. So basically, the novelty is extending the loading and extending material properties to Young's modulus, coefficient of conductivity, and so on and so forth. Now, novelty is also the fields that we have to compute. First of all, we're going to be looking into the non-stationary problem, and everything will be not only a function of x, which is the space coordinate, but also of time. In other words, no stationary problem. We are going to be interested in starting at, let's say, heating at certain point equal to 0, and then heating for a certain amount of time. Let's say weekend, you go skiing and you heat your chalet only for 3 days. So you have a displacement, strain, and stress. These are first 3 for the mechanics. And then on top of that, for the temperature, you will have a so-called entropy. Entropy is not an easy notion to explain. In statistical mechanics, that really is a kind of more clear. This is tendency of the system to go to disorder. It's a measure of disorder. It keeps increasing. They say since universe was created, entropy keeps increasing and expanding and so on and so forth. And the temperature would be a dual variable to the entropy, just like the stress is dual variable to the strain. And basically, it's much easier to comprehend because you simply can measure temperature with your thermometer. And you say, okay, temperature right now might be -4. So it's better to be inside with a heated room than sitting outside at -4. And then finally, the role of heat flux is also something which is important, because this is really what takes heat from one side to another. Heat flux, actually, you will see by Fourier's law, is in the opposite direction of the temperature gradient, as opposed to stress, which is in the direction of the displacement gradient, which is the strain. So there's a minus sign. And that actually is a physical observation, that if you put a radiator in the corner of your room, then the room gets heated, because heat goes from something hot to something cold, as opposed to the gradient, which we go from something cold to something hot. And that's why you can heat. It's actually, heat equation is a wonderful equation. This is so-called the parabolic differential equation. We have first derivative for the temperature, for the time, and second derivative of the space. And it really is a characterized the diffusion type of a phenomena. That is, you start with the peak behavior of your solution, and then kind of just smears out and gets really very smooth. So this is kind of nice. But internal variables like this motion here, these are plastic strain epsilon P, viscoplastic strain epsilon VP, hardening variable Xi, damage variable D. They're characterized with the same type of parabolic differential equation in terms of their evolution in time. In other words, they have a first derivative equal to something. And that something could be like similar to what you get in the heat equation. In fact, again, the computing, the spreading of this internal variable is fully under control. Now, many people are interested in identifying the properties of your material. And that means really that you run your test and you take observation from the test. Then you run your model with the type of model to imagine, and you compare these two results. And in the process, you have to do inverse analysis to understand how this thing actually has been evolving. So instead of solving this evolution equation forward in time, like you normally do, you have to recover this backward in time. So this diffusion coefficient actually is characterized by a exponential or minus something, so it kind of goes down very quickly, whereas backward in time would be exponential or plus something. So if you have only small perturbation, it explodes very quickly. So identification work on the inelastic behavior is notoriously complicated. In fact, nowadays, if you really want to do it better, you don't do it in terms of deterministics framework, but you do it in terms of probability framework, because this is really much better in the sense that you really fully master what can happen in a particular material. We'll talk about that a bit later as we cover all this type of thing. So in the elastic regime, if you have thermal elasticity, I only need these 6 fields: displacement, strain, and stress, entropy, temperature, heat flux. Now, in the inelastic regime, which is our main goal today, you have to add these internal variables. These internal variables are used as a convenient measure of how the structure of the material is changing from the virgin material and how this damage is no longer possible to eliminate. So you have something which is residual or plastic or viscoplastic deformation. You have also hardening variable, which shows that the material gets hardened. And you have like a, I don't know, damage variable that shows that elastic modulus is never the same, and so on and so forth. So we'll cover all this. Let me just illustrate what I really mean by this with the simple sketches. So if we have a elasticity problem, here in particular is presented a stress strain diagram for the nonlinear elasticity problem. So what we do here, we load the specimen and the stress goes up with the strain, which is increasing. And then you say, okay, enough, we finish the test, we reduce the loading down to 0, and the response sigma epsilon follows the same path. It goes down to 0 stress and 0 strain. Now, if you have a plasticity, something like a isotropic hardening, which might be non-linear, so something like a saturation, basically you go linear, let's say for the simplest case, until the yield stress, this is the stress where the plasticity phenomena kick in. For materials like steel, reasonable steel is 400 megapascal and so on and so forth. You can actually, beyond that, have a different response because hardening kicks in, so it's no longer linear. You might have something else like a saturation hardening or kinematic hardening and whatnot. And even if it's linear, it's not the same slope as before because now it takes over something like a hardening modulus as opposed to Young's modulus. And if you don't know the value, typically hardening modulus will take 10% of your Young's modulus. If you know, then you do identification and so on and so forth. So you push this to the maximum level of the loading where you want to go with the test, and then you start unloading. Now, contrary to elasticity, where you follow the same path when unloading and go down to 0 stress and 0 strain, here you start unloading in a way which is exactly the same as elastic. Namely, what happens, I mean, one interpretation of these phenomena is that basically first you kind of introduce elastic deformation, and then you introduce the plastic deformation. In metals, plastic deformation is related to dislocation type of kinematics, where the yield lines are created in the direction of the maximum shear stress. And once you stop, basically this dislocation gets frozen, and you simply unload the elastic response. And so if you unload this elastic response completely, if I were to put this straight line all the way to 0 sigma, you will see that the strain will never be equal to 0. You will have this irreversible or plastic strain, which you cannot get rid of with a normal way. That means your material has been changed, the internal structure has been changed. You no longer have the same ability with your material to carry on in this type of thing. Now, this is plasticity. In the viscoplasticity, it's kind of similar behavior with the yield stress, and after that you have a plastic deformation. Only this time around, the amount of plastic deformation or the kind of value of stress that you can handle depends on the rate of deformation. The faster you load, it appears that you can take larger stress. So here's like an increase of the loading rate. You do it faster and faster and faster. You get these curves which are not unique, but you get a higher and higher response for the sigma that you can measure. And basically the idea is that some people are saying this is a maybe imperfect interpretation, because really what we are measuring is just the force, and we cannot in the testing machine, but we cannot measure inertia force. Yet if you're doing a very fast loading, you know that the proper framework is not static equilibrium equation, it should be dynamic equation of motion. Or you can treat dynamic equation of motion in the spirit of D'Alembert as equivalent static equilibrium equation, but you take inertia forces, which is product of mass and acceleration, on the other side of the equation. That means you take it with a minus sign, and basically then you compare this static response. But then you cannot measure acceleration, what's inside the material. So basically, in fact, this acceleration producing inertial force is really reducing the kind of force that you measure. And so it's not really material that is more resistant, but it's actually the force which is smaller due to the influence of the inertial force. And that is really some people that say. But in any case, right now, we do distinguish between plastic and viscoplastic, and it's not only for physics. For mathematical purposes, viscoplasticity has many advantages in the sense that you can actually handle the like a computation of internal variables, something like that, in a single shot, and has some advantages in that sense. This is so-called the Yoshida regularization. It regularizes the problem and it removes the constraint, and so we'll get to that in a moment. So the final class of problem I want to talk about is this damage mechanics. This is actually when you have a very similar to plasticity, you go to the limit of elasticity. Often here it's called the fracture limit, because you definitely to start observing these cracks. This is typical of representing by a damage model. And then again, you'll have a nonlinear response. Even if you have a linear hardening, you'll see that in moment Y, because damage compliance is getting bigger and bigger, and this thing gets more and more horizontal. And then once you say, okay, enough, I want to start a loading, contrary to plasticity, we unload in this direction of the elastic response. Here you unload in a way that it brings you back at zero strain and zero stress, but the path you follow when you're loading and the path you follow when you're unloading is no longer the same. Namely, material has been damaged and the elastic modulus is no longer intact. So next time you come, you will go this way and go back and so on and so forth. So in all these curves, contrary to elasticity, where you go up and you go down following the same path, so there's no area that is, let's say, covered by these two curves together. Here in plasticity, if you go up and you go down like this, there's area here. In viscoplasticity, it's similar here. And in damage, there's a little bit area here. So this area is so-called dissipation. This is the energy that you've dissipated and that you cannot recover anymore, even though if you have decided to kind of stop loading. So basically, the idea is that we'll have to define this dissipation for different models as we go along, and we'll see how to handle this type of thing. So let me start with the thermodynamics of reversible processes. So first, I will consider elastic case, and I will remove completely the mechanics. In other words, I'll consider rigid conductor, and I will only focus upon a heat transfer equation. That means rigid conductor will have a Young's modulus that goes to infinity, and the formation will be equal to 0. So there's nothing going on in mechanics. I'm just looking to define something like entropy, temperature, and heat flux. All the rest is no longer interest to me. So how do you handle this? First of all, internal energy of rigid conductor you can define in terms of the function E, function of entropy S, But again, I said S is entropy is like tendency of the system to go to disorder, which is kind of easy to say, not easy to quantify, at least at the level of this homogeneous type of thing. Although I'll show you that at the end, you can compute your entropy. So you really have to, as you follow the computation, you have to kind of compute, establish the entropy, at least for the elastic case. But it's actually more handy to not use entropy as a state variable, but rather the temperature. So this could be accomplished by using so-called Legendre transformation and basically do exchange between free energy of Helmholtz and this internal energy. In other words, you can say the psi of theta, which is free energy of Helmholtz, or internal energy EOS. These two are connected with the product between theta and S. It's rather similar to saying that you can have an internal energy, a function of epsilon, and then complementary energy that you can express in terms of sigma, and these two are connected with the product of sigma epsilon in mechanics. So this is pretty much the same type of thing. So this is just a statement which is actually changing the roles between the entropy and temperature, nothing more than that. So from that one, I can only define something that people often call zero principle thermodynamics, which is basically taking the derivative of this function with respect to S. And you can see here you get zero, here you get derivative of E with respect to S, and here you get only theta. That defines you the temperature to be partial derivative of this internal energy with respect to entropy. And we define this temperature to always be positive, not to have a problem with the sign. I think the lowest temperature is minus 273 or something like that. That was ever recorded, and hopefully you're never going to go more cold than that, because they're talking about global warming, not global cold, global freezing. So basically, this is introducing kind of more clearly what temperature is. In fact, if you have a rigid conductor, often we kind of assume that internal energy is simply linearly proportional to the temperature, which is now a function of the entropy. So E of S is equal C times theta of S, where C is heat capacity coefficient. What heat capacity coefficient is, this is the property of a material which quantifies the abilities to store, let's say, energy due to some kind of heating. And then we go to these principles of thermodynamics. What these principles are, they are basic principle of conservation. So first principle is that energy conserved, that whatever you put into your body, it stays there when you have elastic behavior. And what can you put inside in terms of internal energy, that heating? Well, one way you can put it is the mechanical work. I'll for the moment skip that one. This is P. I won't define what it is, but you can also put it with the heating. In other words, you can increase the internal energy of your conductor by taking distributed heating. Let's say here we are studying a 1D problem that is put between the segment connecting x1, x2. So this could be finite length. x1, x2 are somewhere in the length of your conductor. And then basically take internal energy density, E of S, you integrate from x1, x2. This is your total internal energy. And heating is the distributed heating R, integrated from x1, x2. And then you have flux. Flux is considered to be, by definition, outgoing. So if the flux is positive, you're supposed to be decreasing the energy. If flux is negative, you're supposed to be increasing. That's why you have a minus sign here. So now you go to the limit. You take x1 that goes to x, replace it, and then x2 tends to x1, so make it infinitesimal. So from the first example, from the first expression, sorry, I get a derivative of the internal energy density with respect to time, which I can write as dE ds times ds dt. And then from the second one, I get R, and the last one, I get derivative of dq with respect to x. So basically, given that this choice of the internal energy, this is product of C and theta, you can see immediately that basically I can have here that dE d theta would be simply C. And from this one, I get an equation, which is a well-known heat equation, which has heat capacity coefficient C multiplied by the first derivative in time of temperature field plus equal to R, distributed heating function of x and t, plus the second derivative of flux, which is written as a minus k times gradient of theta. So this is like a second derivative of this. Laplacian in 3D case would be k times Laplacian theta and so on so forth. So many mathematical books start with this type of equation to study behavior of the system. And that's actually what we need also to kind of take into account this one. So I will have to switch for a second to basically get this explanation. So Bob, share screen, and I will have this one. So let me now see how I can handle a computation with such equation. So here's the equation. I just changed it slightly. It was a earlier version of my transparencies written in French. So thermic non-stationnaire problem linear. This is linear problems in non-stationary term heat transfer. So you have recognized all the notation. R is a heat source, theta is imposed temperature, H is imposed flux on the other side of the boundary. Then theta 0 is the initial condition of the temperature. Then you have a specific heat, let's say, and then you have a density. Well, either you can express it with a unit of mass or unit of volume. It depends what you do. Here's what the unit of volume. And then you have heat conduction coefficient K. So this was the equation we just wrote, only I called it before C. This is now 0, but it's just a detail, so it could be a single coefficient, doesn't really matter. And so basically, I want to be able to solve this problem. I'm going to be, first of all, writing a strong form to say that I have a defined heat source, distributed heating and function of x and t, impose temperature on the boundary by impose the temperature, theta bar of t, which is the same role as u bar, only now it's not stationary, so it's a function of t. Then he posed a component of heat flux, h bar of t, and then I have theta 0 of x. This is like initial temperature to start with. Then I have to solve this equation for each value of x and t, x in the domain omega. Omega is from 0 to L, and in the interval of time from 0 to uppercase t. All these conditions, theta equal to theta bar, have to be defined of gamma theta, where imposed temperature has to be at least 1. So I can have a unique solution. It has to be defined from 0 to uppercase t. And so goes also for this heat flux that has to be defined imposed value h bar from 0 to uppercase t. Initial condition has to be applied throughout the domain for values of x between 0 and L. And here I have this Fourier law that heat flux is proportional to the temperature gradient, with the coefficient of conductivity being coefficient of proportionality, but with the minus sign because the heat goes from, the gradient goes from cold to hot, whereas the heat propagates from hot to cold. That's why you have this minus sign. You'll see it follows from correctly from the second principle of thermodynamics. So basically the idea goes as follows. I have a definition of this kind. I'm going to use finite element method discretizing space. So first I pick up the, let's say, square integrable function, because again, I have a second derivative just like in the elasticity. So square integrable function will be fine with their first derivative, so it will be square integrable. And they have to obey the imposed temperature at the boundary gamma theta, so that this candidate for the solution theta of x and t, when I fix x to be gamma theta, has to be equal to theta bar of t. And then these weighting functions are only function of x, because basically I'm taking this evolution process in time. I take particular time, and then I try to do weighting residual type of procedure. So when I'm doing weighting residual procedure, the time is fixed. So basically, I take the interpolation of w, just a function of x. And again, it's a square integrable with the first derivative to be square integrable. And the value of this guy at the boundary gamma theta has to be equal to 0, just like a weighting function mechanics. At the place where I impose displacement, this virtual displacement has to be equal to 0. It's the same story. So basically now I plug this into the weakened form of the evolution equation, which is this one here, heat equation. I multiply this by this weighting function. I integrate by parts with the goal of reducing the derivative of this guy, theta. You go from second derivative with respect to x to the first derivative In the process, you recover the first derivative of dw dx, and you recover extra term, which is interpretation of your boundary condition of imposed flux. And so you can compare here. If you neglect the first term here and you replace theta by u and r by b and h by t bar, you will recognize your elasticity problem. So if I'm solving a stationary problem of heat transfer, the solution is exactly the same as a 1D elasticity. So if I have a code only for 1D elasticity, I can put numerical value for, instead of Young's modulus, heat conduction coefficient. Instead of the whatever load, I can put my heating, and the displacement that I compute will be actually the temperature, and I can simply solve the problem, or vice versa, whatever it is. But now when I have a non-stationary problem, mechanics and heat transfer are not the same. In mechanics, you will have a second derivative with respect to time. You have a inertial force, whereas here you have only first derivative with respect to time, and you have this evolution problem a little bit posed differently. So in terms of the interpolations, all these three terms at the end, I know how to handle. The only new term is the last one, or the first one, sorry, where I have to handle this evolution term. So I pick up again finite element method. I take my shape functions that have to be chosen to start with simplicity, 1 at the node A and 0 at all the other nodes. And I construct the weighting function Wx, like the product of Wa, the nodal values of three nodes, times the Na of x, the shape function that I just described. I take the same interpolation for the real temperature field, only it's multiplied by the dA of t, where dA of t is time evolution of the nodal value of the temperature. Given that this shape function I constructed that I just described, that is value 1 at the node, which is A and the 0 and all the other nodes. So after that, I can easily compute the derivative of theta with respect to x, and I get my B operator, which is derivative of Na with respect to x. So I plug that in, and here I recover something that looks very much like a stiffness matrix of the elasticity that was BA times K times B. The only difference is no longer Young's modulus E, but it's a coefficient of conductivity. But again, all the remarks and all the computation of the stiffness matrix we described in detail in elasticity will now be directly applicable here to obtain the so-called conductivity matrix of non-stationary heat transfer. So also applies to the external load. If you replace B by R and you replace T bar by HR, this will allow you to compute your distributed loading. Remember, for a two-node truss bar element, if you have a linear distribution of a distributed load, you need two Gauss points to get a proper value. It will be like 2R1 plus R2 plus, and the second term will be R1 plus 2R2 divided by the length of the element, and this will be like a linear distribution of these type of things, and so on and so forth. Now, all this has been explained. I really should not spend more time repeating it. The only novelty is this guy. So MAV is something called heat capacity matrix. It can be computed as a derivative, or is an integral of Na times rho C, or just C if you want to simplify it, times NB. So this time around, these are linear polynomials. And then you multiply, this could be quadratic polynomials. Again, you won't be able to use only 1 point of integration. You need 2 points of integration. And if you do that, you will have your let's say, approach to the finite element method, and you compute your heat capacity matrix, basically either with a consistent manner. If you take a linear distribution, where this is 2, 2, 1, 1, 1, then times CL divided by 6, or you can diagonalize it. Diagonalizing, that means you take all the coefficients, you put them on the main diagonal, so 2 plus 1 is 3, 2 plus 1 is 3, and 6 divided by 3 is 2, so that becomes rho CL divided by 2. It's basically the same thing goes for dynamics, only M will be, let's say, a mass matrix. And so this diagonal version is very suitable when you do explicit scheme. We'll come to that in a moment, because it really simplifies the cost of it reduces the cost of computation tremendously. And also even turns out to be better as approximation. And so one often does that quite handily. So basically, going back again here, I have discretized respect to x, and I can say that my Galerkin equation, this time for non-stationary heat transfer problem, could be written as the product of these three values of the weighting function Wa multiplied by the residual. So residual is written here. It's a heat capacity times the time derivative of the nodal layer's temperature, plus heat conductivity times the nodal layer's temperature minus the external force time the variation. So I can say if this has to be equal to 0, then I can say for any arbitrary value of WA, I will require that every RA, every residual component has to be equal to 0. So basically, I come down to not this time to a set of algebraic equation. I come to a set of the ordinary differential equation, which are parabolic, that you have n times d dot. D dot is the first derivative of the nodal area of temperature with respect to time, plus k times d equal to f external function of t. And so basically, the question is to find the solution of this equation for the values of time from 0 to t. So contrary to a static problem in elasticity, I do not come with the finite element method to something that I can solve directly. I mean, this time around, Gauss' method will not do it because it is no longer a set of algebraic equations. Well, here it's written only one, but it is set of an ordinary differential equation time. So it's either I take an analytical solution to solve this ordinary differential equation time, or I try to do something better, and basically I go for the time integration schemes. Or in French, it's called schéma d'intégration temporelle. So for a non-stationary heat transfer, I'm studying a problem of this kind, where I have a capacity matrix M times the first derivative of the nodal area of displacement, plus the Hoyt conductivity matrix K times the nodal areas of the temperature, sorry, equal to f of t, and I have to get the values from 0 to uppercase T. The initial condition of temperature would give me the initial condition of these 0. Basically, by integrating, by discretizing this in the same manner, and using this value of theta 0, which was given here, I can recover the d0, which is the initial value of the nodal areas of temperature when time is equal to 0. So the way I'm going to do that is by using time integration schemes that take into account only one step at a time. In many software, really this is the by far preferred choice. When I was studying these things at Berkeley, that was with the people who are mathematicians with really not worrying about only finite element method, but all kind of mathematical aspects. And one of the key books at that time was Gear. It was like ordinary differential equation, how to think at time. And they really enjoyed doing a multi-step scheme. That means you take many steps to get to the time Tn plus 1. So basically, that is the idea that you want to say. Let me just take a quick break. I'll come back in a moment.
We are fine, Professor.
I do have a question, actually.
Please do, yeah, go ahead.
There are two moments in which you define the constitutive equations, and this is an imposition in how to derive the constitutive equation from the free energy, or is it a result? I did not get it.
Basically, we will see this in a moment when we after the break. I advocate always like defining inelastic model for your material, your structure, and so on, by certain ingredients. So if it's plasticity, you have anti-decomposition of total deformation to plastic elastic. Then I have to define free energy. So free energy is the one that I define for my material. And then I have to define a yield condition. So these are three basic ingredients. We'll see that in a very systematic way over and over. So hopefully that will enter. Once you do it more than once, you can see that it's always the same trick. It's just a variation of plasticity, damage, whatever, add this, add that. And so basically the defining the behavior of material, you can do it with a free energy, which can define at any different scale. You can define macro scale and micro scale, and we'll do that as well. So, some people are saying, I remember listening to some of my, say, classmates from Berkeley, although we never met because they're older than me. This guy, Ortiz, was doing that. He was calling this garden variety of potentials. You have, if you look into the typical journals where material people are publishing, like, for example, Journal of Mechanics and Physics of Solids, all the material doing homogenization people are publishing there. They have a huge choice of these different potentials. that are justified more or less by different microstructure and so on and so forth. So easiest way of defining the constitutive behavior of material would be through the free energy. This way you can accept that you have a potential, and it's very good for the computation, because then you can handle computation in a better way. That is the key point. So hopefully, but we'll go along, and you'll see that, you can hold your question until the end of this, and hopefully we'll cover enough that it kind of more meaningful to what I'm saying. Right now, it's just like, talking without showing what we really talk about. Okay. Any other question? Or fine. So let's take 15 minutes, 10:20, let's say 10:35 or 10:36, because a minute. Okay. Guys, see you 10:36. So let's go up. Okay, shall we go on? Everybody up. Let's go on. Everybody back. Good. So we said that the dissipation, which is the key point, is defined as the time evolution of the eternal variable that you have to be defined with respect to type of phenomena we're trying to capture in terms of inelastic behavior, and the conjugate flux, which is computed as the partial derivative of the free energy with respect to these internal variable. And in particular, we'll take, let's say, Gibbs potential, which is a function of the stresses, temperatures, and internal variable. And basically, what we do here, we can obtain that the constitutive equation defining the strain as the partial derivative of the Gibbs potential with respect to stress, defining the entropy as the partial derivative of Gibbs potential of the temperature. And then we have to kind of, in elastic process, we are done because we can kill the evolution of the internal variable. And we simply have a reduced form of the first principle to compute anything we need along with the remaining equation. In the inelastic process, the key point is we need evolution equation that comes defining internal variable as a function of stresses, temperature, and internal variable themselves. And then we can define dissipation given this evolution, given by this function f alpha for any internal variable psi alpha, multiplied by the corresponding flux. So if you have the potential, if you have a, let's say, evolution, you can always get the corresponding dissipation. So how are we going to approach that? Let us first do that in a simple way. Another way, I'll go to study a very simple case on 1D problem, where basically I can obtain something called rheological model. So this is maybe too complicated. Let me again stay with a simple illustration. So if I have a elasticity, remember the type of problems I gave you. So this is like a truss bar where I actually built in this end and I pull it on this size. We call this T bar. And then basically the length of the bar is equal to L. And we characterize behavior of the material in 1D case by Young's modulus. We have a cross section A, which is not necessarily equal to 1. We can have a loading, but this time I won't apply any. We can have a post displacement, I won't apply any. And we can obtain here the displacement at free end, which is U of L, up U of L, versus the T bar. This is applied traction. And I can make a diagram for linear elasticity where the response is a straight line. What the slope is, if this is 1, this would be E times A divided by L, okay? Now, what we'll do, we'll construct something called rheological model. This is a very easy problem. I can solve this statically determined problem, obtain stress field from that strain field, and then integrate and get displacements. So I won't bother because we've done that already. So imagine I'm going to take a case where A is equal to 1. So this is usual decision when I'm making 1D problem. I'm going to take the case where L is equal to 1. So instead of this guy, when I divide by A, this becomes sigma. And if I divide this by L, this becomes my epsilon. And L equal to 1, A equal to 1 is kicked out. So there's only a guy which is left giving me the slope is the Young's modulus. So sometimes you write this rheological model as a spring. And the spring has a unit length. And it's loaded by sigma because T bar becomes equal to sigma given that A is equal to 1. And then the displacement here is the same as epsilon. And you can see the typical elastic response is that basically you are stretching the spring, and this is actually called the epsilon or epsilon elastic if you did. Now we can do something called linear elasticity, viscoelasticity, because this is already linear elasticity. So the most general case of linear viscoelasticity is the one where I can have one spring, and then in the series connection, I can connect this with the second spring, And here I can put a viscous damper. All these guys could be a function. I forgot now what is it called. Doesn't matter, I might made a mistake, but it is, I think this guy is E0 and this is E1. Both of them could be function of temperature. So this is function of theta if you want, or so on. And this is a viscous damper, which also could be function of theta. So this material is characterized only by Young's modulus, and this is called linear elasticity, where this material is characterized by E0, E1, and eta. And this is kind of generalized Kelvin-Maxwell material and so on and so forth. Again, the whole thing is here equal to 1. I have a sigma, which is applied, and I have here directly epsilon. So this is the kind of situation I'm going to face here. Here it is my, well, I always get it right. So this is E0, only E1 is down, but doesn't really matter. So you can see here that at any section I decide to cut this, there only will be one stress component going from free end, where I apply this stress component, to the built-in end. In order to keep equilibrium, sigma is constant at any value of x that goes from 0 to 1. And then if I stretch it, of course, I'll have my epsilon to me a deformation. So I can see intuitively, if I keep this fixed, whatever is the way I can keep it fixed, let's imagine for the moment I can do that. The only thing which stretches is this elastic spring E0. So I will call this elastic deformation. And then basically the elastic deformation times E0 is equal to this sigma. And then I can fix that part and I can stretch this. So I will call this viscous deformation. And basically by stretching this part here, this elastic spring will stretch. So the sigma will be E1 times epsilon viscous. But also this viscous damper will enter. And this one is proportional to the rate of viscous deformation. It will be eta times derivative of viscous deformation with respect to time. So basically, sigma, which is shared throughout this one, it could be either represented like this or like that. So I go back to the story. So this is the simplest model of, let's say, inelastic behavior. It's called linear viscoelasticity. It has one internal variable, happen to be viscous strain. As I said, this is the formation of this viscous damper. And basically, I can say that the total deformation is split into the elastic. This is the deformation of this spring E0. And viscous, this is the formation of spring E1 and viscous damper. And then basically from the first part, where there's cutting here, I can obtain that the elastic deformation is equal to sigma divided by E0. And then from the second part, where these two act together, I can obtain something that looks like an evolution equation that I needed, where this internal variable is a function of the stress, temperature, and internal variable itself. And that's precisely what I get. With sigma is equal to E1 times epsilon viscous plus eta times derivative of epsilon viscous with respect to time. From such an equation, I can obtain the derivative of epsilon viscous with respect to time is equal to 1 over eta times sigma minus E1 divided by eta times epsilon viscous. Given that eta and E1 are a function of theta, you can actually obtain something that looks like a generalized evolution equation that we are looking for. We obtained this from the rheological model for 1D case, which has been really obtained by simplifying the type of solution that we already obtained for linear elasticity. So many people, when they develop these different behavior of materials, they use this rheological model as an easy way to understand behavior of particular material. Rheological models are useful as a teaching tool to understand really first understanding of this thing. But in reality, in 3D case, it's not so easy to obtain such a rheological model. In that case, we'll see this. We have more generalized approach. Once we define dissipation, we can then appeal to something called principle of maximum dissipation into plastic or damage and so on and so forth, and obtain this evolution equation rigorously without appealing to any rheological model. Just once we define the type of the ingredients that you need for an elastic behavior. At this stage, we are fine. So this is linear viscoelasticity. It's actually something that is very well known because these are the first type of model that people used. When you kick out E0, you get something called Kelvin model. This is a spring and this dashpot or this viscous damper in parallel connection. And then if you kick out E1, this is so-called Maxwell model. This is spring and dashpot in series connection. and either of those were used, not very successfully, because typically if you really want to describe something like a creep or whatever other type of time dependent deformation of complex composite materials, you typically need nonlinear dependence, not just linear dependence. But in any case, what is important here, given that you have evolution of stress, you can obtain the solution of such an equation and say that the viscous deformation has certain evolution which is quantified by the, let's say, characteristic type of evolution time, which is tau, which is ratio between eta and E1. So as I said, if you really want to have a validity of your thermodynamics for inelastic to constitutive behavior, you better have this very short compared to the stuff that is really a typical evolution equation for other stress, for other state variable like stresses, temperature, and so on and so forth. In this particular case, here it is that you can obtain, again, the dissipation is simply derivative of the free energy with respect to viscous deformation multiplied by the evolution equation we just obtained for this stuff. But linear viscosity, other than giving justification for something like a Rayleigh dumping, which is not really physical model of dumping, does not have much practical application. So we switched to a little bit more interesting one. That's called viscoplasticity as opposed to viscoelasticity. What I have changed in these rheological models here, I have kicked out the other spring, E1, compared to this viscous part, and I replaced it with a frictional slider. This frictional slider is appealing to the equivalence between plasticity and friction. That is, you don't do anything unless you reach certain level, which is called limit of elasticity, and after that you start plastic deformation. This is like, you know, you don't slide until sigma is equal to sigma y, and after that you start without any resistance. So this is the role of this plastic slider. So E0 need not be called anymore E0, it will be just called E. And basically I have now the material which is characterized by Young's modulus, which is usual case for elasticity, then sigma y, which is limit of elasticity. That's where I start this viscoplastic deformation, and eta, which is this viscous damper that is giving you the change of let's say, stress when you go over certain value, which is so-called overstress, when you go over the limit of elasticity. So basically, again, the deformation goes as follows. When you just stretch the elastic spring, we'll call this elastic deformation, and you can do that as long as sigma is less than sigma y. Once sigma reaches the value of sigma y, the slider starts sliding without any resistance anymore, and basically all the stress, it's called overstress, sigma minus sigma y, is taken by the viscous damper. That means now sigma minus sigma y should be equal to eta times the epsilon viscoplastic dt. And that's actually what we have here. From that one, I can obtain that my viscoplastic dt is equal to, it was written again in terms of this period of relaxation tau, is equal to e to the minus 1 divided by tau multiplied by overstress, which is the sigma, which is absolute sigma times sine of sigma, minus sigma y times sine of sigma. And then basically you have this evolution equation again for the eternal variable, which is here viscoplastic deformation, which is expressed in terms of all the variables, that's the sigma, theta, and epsilon. At a certain point, now here already we dropped theta. Once we understood how to define dissipation, thermodynamics giving us this will. For the moment, I just dropped the theta, and then we'll carry on without that, either considering that this is temperature is considered fixed or entropy considered fixed, either it's isotropic, what do you call it? The thermal conditions are fixed or adiabatic conditions are fixed. And then in chapter 7 of the book, you have going back to really thermomechanical coupling or thermodynamics and computing everything evolution as it go along. But for the moment, if you want to focus about elasticity, once the thermodynamics taught us how to define the inelastic dissipation, this is enough to kind of drop the temperature. So here we have this period of relaxation, which is giving really significance in terms of physical tests. Namely, if you take a viscoplastic material and you stretch it beyond limit of elasticity being a sigma y, the stress where you start yielding divided by E. So it's epsilon 0, it is a quick kind of stretch that you start initially and you stretch it beyond that. The stress will be bigger than sigma y because you have this viscous damper that can react. But then in time, it is going to relax down to sigma y. And basically, how quickly it is going to relax, it's decided by this period of relaxation. And again, recall, if you want thermodynamics to be valid for inelastic processes, what you have to do is that this period of relaxation be much shorter than the typical testing. So you increase the stresses and temperature, maybe keeping constant. You increase stresses very slowly, so the period of change of these state variables is small, but then yielding and so on becomes very fast. And then thermodynamics should hopefully still apply. That's actually our goal. So if you really want to make sure that you have a very fast change of internal variable, then you don't go for viscoplasticity, you simply go for plasticity. So viscoplasticity, we had this viscodamper, and period of relaxation was eta divided by E. So if you want to get period of relaxation equal to 0, that means it's instantaneous. So basically you get something called perfect plasticity. You simply remove the, what you call it, the viscous damper, and you put in the series connection your elastic spring and your slider. In this way, you have something called perfect plasticity, not because it's perfect, but this is the first type of thing that was kind of the simplest you can imagine. In French literature, with the very well-known books of Nigan Coxon, they were doing this with Germain, who was the professor at École Polytechnique. They call this standard materials. This is a perfect plasticity. That means you have, like you'll see in a moment, you have internal energy, and also you have energy potential, and you have like a yield stress, and so on and so forth. And the evolution equation also obtained from this yield condition and stuff like that. So there's certain, let's say, symmetry in this type of structural stuff, and they call it standard. And you have a hardening, they call it standard generalized material, and so on and so forth. But it's really the same thing as I'm explaining here. So basically, in this case, when you have a perfect plasticity, the material is characterized by Young's modulus and yield stress, only two coefficients. And you have actually stress which can go up to sigma y, and then it starts sliding without resistance. So if you want to obtain this sliding without resistance, this is called plastic deformation. And basically, you need an evolution equation for plastic deformation to be functional sigma temperature if you have it, and the internal variable, which is plastic deformation itself. So basically, the idea is like from the Gibbs potential, I can obtain cos-theta equation of the strain. And I can say if the elastic response, that is elastic compliance, d epsilon d sigma, and thermal, let's say, deformation, d epsilon d theta, are independent of internal variable, which happen to be case of something like this metal type of materials. Basically, you can say that we generally accept that the total strain is then split into additively for small strain setting into elastic strain, which is only functional sigma temperature, and then plastic strain, which is only functional internal variable, which is itself a plastic deformation. So basically, with this additive split, this is the first condition that we take when we quantify plasticity, that the total deformation is equal to the elastic and plastic. The second ingredient that we need to define a potential. So for a perfect plasticity, we can define potential to be like elastic part, which is dependent on the elastic deformation. So this is the energy that is stored into elastic spring. Recall there's elastic spring, and then you're basically applying deformation. You can store energy into this elastic spring. What is the energy? Like in the total, let's say, case of the linear elasticity, the total stored energy is 1/2 epsilon times E epsilon. Now in the perfect plasticity, instead of epsilon, we'll just have epsilon elastic. And epsilon elastic happens to be epsilon total minus epsilon plastic. So it will be like written here, 1/2 epsilon minus epsilon plastic times E times epsilon minus epsilon plastic. And then the only internal variable is the plastic deformation. This is a sliding of this frictional slider. And basically what we can have is basically that starts with the value of this slider, sigma is equal to sigma y. And basically you can obtain from this one the definition of what is the stress. This is derivative of the free energy with respect to epsilon. So that becomes E times epsilon minus epsilon plastic. In other words, this is Young's modulus times the elastic deformation. And then since these total and elastic plastic deformation appear together, only with the minus sign, it turns out that the energy conjugate flux that drives the plastic deformation is simply negative value of stress. So the plastic deformation then becomes, for this perfect plasticity, a product between stress and the time derivative of the plastic deformation. And from this one, you can define our plastic, let's say, dissipation without any kind of logical model, simply by following the rules of let's say, thermodynamics that you already discussed. So basically, this is the type of thing that you will have in perfect plasticity when you're cycling the loading. Basically, you can, let's say you impose the stress until sigma y. When you reach the value sigma y, material is no longer stable. You have something called Drucker stability. You have to control now the imposed deformation or imposed displacement, and then you can slide this as much as you want. And basically after that, you say, okay, enough of sliding, I start unloading. So the stretch elastic spring, which already took the maximum elastic deformation before it started sliding this slider, will then unload. You will recover elastic deformation, but you will move the slider to new position, and you have a plastic deformation you cannot eliminate. Then you push it, let's say, in compression, then you can reach the value of sigma equal to minus sigma y, and then you'll push it to the right, and then basically will accumulate again the sliding, and you can go around the cycling the way it is shown here. So basically the goal will be now how to get evolution of this plastic deformation in terms of some equations. So for that reason, I will focus upon the simplest rheological model that brings this plastic deformation. We simply have this frictional slider. So the stress strain diagram, sigma epsilon is given here. Stress is equal to a relatively unknown value between 0 and sigma y, as long as deformation is equal to 0 and either smaller than epsilon y, which is sigma y divided by E, which is smaller than sigma y, or bigger than minus sigma y. In fact, this is something called, in fluids, this is used as a so-called Bingham fluid, where you neglect the elastic deformation and simply use let's say, plastic deformation. So if you now want to get the behavior of such a, let's say, plastic deformation, because now total deformation is simply plastic deformation, so you can say that plastic deformation could be equal to some kind of parameter, epsilon plastic dot, would be derivative of plastic with respect to time, would be equal to gamma dot when sigma equal to plus sigma y. And this is positive. And then if you want to keep this gamma dot positive, you can then call this to be epsilon plastic dot equal to minus gamma dot, with sigma equal to minus sigma y, which is negative. So I can write these two together by saying that epsilon plastic dot is equal to this gamma dot, often called plastic multiplier. You'll see in a moment why is it called plastic multiplier, times sine of sigma. And so it happens that this can be formally represented in terms of so-called yield function or criteria when it starts yielding, basically saying that when phi of sigma is equal to absolute value of sigma minus sigma y, and that function takes value 0, in that case, my gamma dot is positive, and I have plastic deformation, it's equal to gamma dot times sine of sigma. So it's either positive if sigma is tension, or it's negative if sigma is compression. So this gives me this evolution equation that I need to compute. If I want to extend this evolution to the elastic regime, then I can introduce the notion that gamma could be equal to 0, gamma dot could be equal to 0. That means there's no change of the plastic deformation. This is the case when I'm unloading, for example, like here, when I'm unloading in this case, or it could be the case when I'm still elastic. In this case, there's a plastic deformation of 0, it will stay 0 until I reach sigma y. Or in this case, plastic deformation, this value, it will change, it will not change when I'm completely unloading. So basically, if I want this to be extended to the elastic case, I can say that in this case, gamma dot should be equal to 0. That means there's no change of plastic deformation, and phi should be negative. In other words, absolute value of sigma should be smaller than sigma y. And so basically, then I can take these two conditions together and produce something called the loading-unloading condition, which says that it's either phi, which is negative and gamma is 0, or phi is 0 and gamma is positive. In other words, product of gamma dot and phi is always equal to 0. You'll see in the moment these are called Kuntake condition. Well, here's the moment that we talk about that. So for the perfect plasticity, we already said the plastic dissipation is defined by going through this definition of the dissipation as a product between the rate of the plastic deformation, epsilon p dot, and the energy conjugate flux, which is a sigma. And then we can say that we can obtain evolution equation by appealing to something called principle of maximum plastic dissipation. In other words, if you start having damage in the inelastic behavior material, in other words, when the things go wrong, they go wrong the worst possible way, then you kind of maximize this plastic dissipation. So if I want to maximize plastic dissipation, it is the same as minimizing minus plastic dissipation. And this should be done under condition that phi of sigma is equal to 0. I did it immediately generally, but should have been better to do it with the case when you don't consider gamma other than for plasticity. So if this thing is supposed to be only restricted to the value of phi of sigma equal to 0, I have so-called constraint minimization. And constraint minimization of the function could be obtained by method of Lagrange multipliers, where you take the function to be minimized, and then on top of that, you put constraint. In this particular case, this is phi of sigma equal to 0, and you multiply this by Lagrange multiplier. And then you obtain the minimum for the constraint function, which is not necessarily the same as the minimum of the full function. But by using this Lagrangian approach, I remove the constraint. And now I can have like two variables. I have sigma and gamma dot. And that's precisely what we're doing here. For the moment, consider just the case when gamma dot is positive. So basically, if I want to minimize this case, that actually turned out more strictly, you have this into very nicely explained in the books of Lundeberg on the optimization problem, and then Stanger with something like introduction to Polar mathematics, something like that. Basically, you have this you can obtain this by taking partial derivatives. So if you take partial derivative of this plastic Lagrangian with respect to the sigma, you can get back your evolution equation to be epsilon plastic dot equal to gamma dot times d phi d sigma, where d phi sigma is nothing but the sign of sigma. That's the part here. And then you can take in derivative with respect to gamma dot, you get back your phi, and you can complete this type of thing in the total set. And you can see that you can get the same evolution equation as those that you obtained from the rheological model. Now, if you are cruising this type of elastoplastic behavior, there's one thing when you are elastic, so there's no change of plastic deformation. And then another thing is when you are plastic. So imagine the situation where the time t, from going from 0 to uppercase t, you have a situation where phi of sigma of t is equal to 0. Then you ask yourself, what happens the next increment? That is t plus dt, where dt is a small value of time. So it could be two choices. Either I'm somewhere here, and I keep staying on the plastic behavior. It could be here, or it could be there. Or it could be one of these where I never really left the elastic domain, or I start unloading. So what's the difference between those two? Basically, I have it here. I can say that if I compute when the phi of t is equal to 0, that means I was plastifying at time equal t. I ask myself what happens in phi t plus dt. So I can take a Taylor formula, assuming smoothness of this function, to be phi of t, which is already 0 because at time t I was plastifying, and then phi of t dot, that is time derivative with respect to time, plus the terms that are of the order of dt squared and so on and so forth that I can neglect. So there's one possibility is that phi of t plus dt is equal to 0, in which case I know I'm still plastic. Or there's another possibility where phi of t plus dt is negative, in which case I know that it is actually unloading. And so what is of interest to me is the case where the first case, where I'm still plastic, because in that case I will have to see what this gamma dot should be. So this is rather easy. I take phi. Phi was, recall there, phi was was the absolute value of sigma minus sigma y. So derivative of phi with respect to time is, first of all, sine of t multiplied by sigma dot, which is e times epsilon dot minus epsilon plastic dot. That's precisely what we got here. So here we have a d phi d sigma, which is sine of sigma, times sigma dot, which is equal to e times epsilon dot minus epsilon plastic dot. Then you take what epsilon plastic dot is, which is a gamma dot times d phi d sigma, and you plug it back into this equation and obtain that 0 should be equal to d phi d sigma, which is sine of sigma, times e times epsilon dot minus gamma dot times d phi d sigma, e d phi d sigma. Given that d phi d sigma is just sine of sigma, so sine of sigma squared is always plus 1, you will have basically that gamma dot is equal to, here it is the final result, that this is epsilon dot divided by d phi d sigma. So you take this value for gamma dot now, you know what the evolution is, you put it back into your stress rate equation, and you obtain that sigma dot is equal to e times epsilon dot minus gamma dot d phi d sigma, which could be worked out explicitly. Either it's e times epsilon dot when you're elastic, or it's 0. In other words, what you're actually saying is that in this type of elastic plastic behavior, either you're climbing with the E, or you're going down with the E as a slope, or your sigma is constant. That means sigma dot has to be equal to 0. That is as simple as that. So this is the case of perfect plasticity. In summary, I have my constitutive equation to be sigma equal to E times epsilon minus epsilon plastic. And then I have epsilon plastic to be equal to gamma dot times sine of sigma. I have yield function to be absolute value of sigma minus sigma y. Loading, unloading condition, gamma dot positive 0, phi negative 0, gamma dot times phi equal to 0. And plus this conditioning condition saying that phi dot equal to 0. That gives me the possibility to compute my gamma dot for the case when I have a plasticity. Now, this perfect plasticity may be not good enough to study because if you really take a true experiment and you neglect this, what I was saying, that sigma epsilon sometimes is obtained in a shady way by ignoring that you have a change of cross section in necking and that the distribution of strain is not the same. What the hell? Put all this in the side. Typical stress strain diagram for plasticity is like this. So you have a limit to elasticity. That's the first time it starts yielding. For some type of material which had been hardened by a technological process, sometimes it's not clear. You don't really show that clearly this elasticity limit, but rather they consider by convention that the elasticity limit is something with the irreversible deterioration is no bigger than 0.2%, which is kind of funny, but that's the way they take it. And then after that, when you start limit to elasticity, you can have a plasticity phenomena. First, you start kind of yielding a lot, and then you kind of recover the structural material, the material reorders and gets hardening phenomena. And then you have something called the threshold of plasticity because the first time you start yielding, and when you stop plastic deformation, then you go back to that, material has hardened. So for example, if you go like that, you climb in the plasticity, then you unload, and then you load again. Basically, you go back to the 0.2 rather than 0.1 because material already hardened, and then you carry on with the free and so on and so forth. So if I really want to be able to describe behavior which is beyond perfect plasticity, but take into account the hardening phenomena, which are characteristic of many real materials, I need an extra variable. So basically, this will be so-called hardening variable. So this is the kind of model that I'll look a little bit more in detail. Rather than perfect plasticity, I'll take plasticity with isotropic, linear isotropic hardening in particular. So it has two internal variables. The first one is a plastic deformation, and the second one is hardening variable. So my free energy potential, I need three ingredients. I need additive split to total deformation to be, again, the same elastic and plastic. Then I need free energy. This is now built by using the same one from perfect plasticity. This is 1/2 elastic deformation times Young's modulus times elastic deformation. And on top of that, I have 1/2 hardening variable times hardening modulus times hardening variable. Hardening modulus is another material parameter. For such a material, I need parameters which are Young's modulus, yield stress sigma y, and hardening modulus k. If you don't have this value, often people take 10% of the Young's modulus and so on and so forth. So basically, then I need yield stress, and I need basically to obtain the yield criteria. So basically, the idea is that the yield criteria is the absolute value of sigma compared not only against sigma y, but again, plus hardening modulus k multiplied by the hardening variable psi. So this really increases the value of the threshold of plasticity rather than yield. So I'm just representing it as a straight line, but the slope of this line you will see in a moment is not k. It was something that has both contribution from Young's modulus E and hardening modulus k together. So these are the ingredients. I have additive split of total deformation to elastic and plastic. I have a free energy, which is constructed as a part of the perfect plasticity and the hardening part, and I have my yield criteria. Now, first of all, I can compute my dissipation. It so happens that this time around, dissipation is not only the one for the perfect plasticity, this is sigma times epsilon plastic dot, but there's also the contribution from the hardening variable, dxi dt, multiplied by the conjugate flux, which is the derivative of this hardening variable with respect to a derivative of free energy with respect to hardening variable, which is simply, for this case, equal to minus k times psi. You can see that directly. So if this q is equal to minus k times psi, I can basically rewrite my yield function as a function of this dual variable. So instead of psi, I can put this q. And this is also handy when I'm doing my principal maximum plastic dissipation. So these are three basic ingredients: additive split of total deformation to elastic and plastic, the free energy, quadratic form into elastic strain and hardening variable, and then yield criteria, which is written in terms of dual variable sigma and q. So after that, I simply follow the rules. I take the principal maximum plastic dissipation. This time around, I have a little bit more elaborate expression of plastic dissipation. I have sigma times epsilon plastic dot, and I have Q times psi dot. So I'm maximizing this under condition that the phi of sigma and Q has to be equal to 0. I'm turning this into the Lagrangian, plastic Lagrangian, which is a minus dp function of sigma and Q plus gamma dot times phi, which is still constraint. And then basically I'm taking my partial derivative to get the constraint minimum. So taking partial derivative with respect to sigma, I obtain the evolution equation of my plastic deformation to be epsilon plastic dot equal to gamma dot times d phi d sigma, which is nothing but sine of sigma. Then I take the derivative of plastic Lagrangian with respect to Q. And recall here, Q is just here with the plus. So you take a d here, dq, there's nothing else but 1. So that turns out that plastic deformation is equal to evolution, psi dot is equal to gamma dot. In other words, this hardening variable could be considered as equivalent plastic deformation. The more you cycle, the bigger is the plastic deformation. So whether I do cycling in compression or in tension, I keep adding plastic deformation. So in general, linear hardening with this type of plastic, let's say deformation, equivalent plastic deformation of hardening variable is not good for cycle plasticity. And you keep adding the value of the stress more and more, which is not justified for real life material. But for static problems, it's quite fine. For some cases, instead of, as much as plastic deformation is kind of intrinsic because it's really what you get when you unload, this is called plastic deformation. The definition of the hardening variable is something that is much more open. So you can take, like we do here, equivalent plastic deformation, but you can also take equivalent plastic work, in which case you can get evolution of this hardening variable to be like gamma dot times sine of sigma times sigma, which is absolute value of sigma. It's just a little bit change of scaling. Other than that, it's still measure of how much you're hardening. Actually, for some work that we've done in plates, it turned out it's better to do equivalent plastic work for this work on 1D, 2D, and 3D type of continuum mechanics models for plasticity. Is fine enough to have equivalent plastic deformation as your hardening variable. And then taking the partial derivative with respect to the gamma dot, you get back with your constraint. And if you extend that gamma dot could be positive or 0, then you can get all the way to that is phi negative 0 and product between gamma dot and phi equal to 0. So, you know, I don't have to make a rheological model for this type of structure. I have simply followed the rules that we applied. That is the composition of total definition elastic plastic. I postulated my free energy and I postulated yield condition, and I obtained everything I need in terms of evolution equations and so on and so forth. So basically consistent condition that we just discussed. When you're yielding at time t, you want to make sure that you're yielding at time t plus dt. That means phi dot phi derivative with respect to time should be equal to 0. So this time around you have not only sigma dot to take into account, 8 times epsilon dot minus epsilon plastic dot being gamma dot times d phi d sigma. You also have q dot, and q dot being minus k, go back here, times psi dot, and psi dot is nothing but gamma dot. So basically, when all is said and done, you can write equation like d phi d sigma times e times the epsilon dot minus gamma dot times d phi d sigma e d phi d sigma plus d phi dq k d phi dq. So given that d phi d sigma is sine of sigma, this cancels, it's simply 1. D phi dq is equal to 1. That cancels, that you are left here with E plus K. And taking this back into your equation, you get stress rate constant equation to be sigma dot equal to E times epsilon dot. And when you have elastoplastic behavior, this is EK divided by E plus K times epsilon dot. So maybe I'll leave you the job for your homework to try to find a rheological model for elastoplasticity with hardening and to make sense out of that in the spirit of the previous rheological model. This will be kind of quite useful for you to kind of handle. So basically, this is the stress rate diagram for the elastoplasticity with linear hardening. I have an elastic response, which is E until sigma y, and then I have a EK divided by E plus K for the elastoplastic response. When I stop and I unload, I have my plastic deformation opposed to elastic deformation. If I go in compression, I have a similar thing, and so on and so forth. So you can see when you start kind of cycling again, you might have adding too many. But anyway, we'll for the moment only study the static type of problems, so we don't worry about cycling for the moment. We'll do reparation later. So here, in summary of elastoplasticity with linear isotropic hardening, what we have is a constitutive law that defines the stresses as the product between Young's modulus and total strain minus plastic strain. And then this hardening variable Q, which is the product between the hardening modulus and hardening variable psi, which is equivalent plastic deformation. Then we have two evolution equations for the plastic deformation to be gamma dot, plastic multiplier times sine of sigma, and for the hardening variable to be psi dot simply equal to gamma dot. Then you have a yield function, which is function of these dual variables sigma and q to be absolute value of sigma y minus q. And we have loading and unloading condition that gamma dot is always positive 0 and phi is always negative 0, and the product with gamma dot and phi is equal to 0. And plastic condition to be phi dot equal to 0, which allows us to compute our plastic multiplier. So basically now we want to study a little bit how to solve a problem where we have a elastoplastic behavior with linear isotropic hardening. And we'll do that for a simple truss bar problem. The only difference now is not going to be elastic, but we elastoplastic. Again, we make a choice of the coordinate system such that the x-axis is placed along the axis of the bar. We simplify the one by saying that we can go for 1D model by cross-section we into a unit value. And the only difference from what we have when you have elasticity, now there's a presence of plastic deformation. Plastic deformation is not only a function of x, it can vary along the bar, but it is also a function of time. In other words, time is called t, but it's in reality called not time, but pseudo time, because even if we neglect the inertia effects that you don't have to take into account very fast loading and all the rates that are imposed in this case, you just need to describe your loading program very precisely, going with some kind of parameter that defines how you go from 0 to the uppercase T when you stop with the loading program. So the role of this pseudo time is to describe your loading program in a precise manner. And then plastic deformation is a function of pseudo time because it's not the same if you're simply loading or if you're doing several cycles of loading and unloading. The plastic deformation is not likely to be the same, especially if you're crossing into plastic, let's say, region several times. So as long as plastic deformation is a function of time or pseudo time, then everybody else becomes function of pseudo time, in other words, displacement, stresses, and so on and so forth. Other than that, I can still keep the equation that I had that are valid for any type of behavior that is kinematics and equilibrium. The only difference now, kinematics, the total strain epsilon is a function of x and t, and it's computed not as the ordinary derivative, but as a partial derivative of displacement, function of x and t with respect to x. And then equilibrium equation, again, it's not d sigma dx, but it's partial sigma, partially with respect to x, because function of x and t, and then plus b, which is again function of x and t. Again, t would have to be specified to give the exact loading program that we need. Then I can take a cos theta equation for linear hardening that I just got. So sigma is equal to E times epsilon, total strain minus epsilon plastic, the plastic strain. And then I can say either I can get my computation in terms of this stress rate equation. In other words, having like elastic domain when gamma dot is equal to 0 to be E times epsilon dot to get my sigma dot, or to have a sigma dot as EK divided by the sum of E and K times epsilon dot when gamma dot is positive. Or I can go with this computation to have this evolution equation for plastic deformation epsilon dot to be gamma dot times C phi sigma, xi dot equal to gamma dot, with the phi which is negative 0, gamma positive 0, gamma dot times phi equal to 0. So this is the kind of computation that I want to do. And basically, I'll start with my finite element method again. And again, I have my imposed displacement on one side. So basically, let's say I have here at the length at the side x equal to L, and the free end I'm imposing displacement, so I can keep the stability of my specimen. And on the left hand, I impose some kind of fixed displacement to be equal to 0, and I stop there. This time around, I have to define what is the state of material. In other words, there's a plastic deformation, there's a hardening variable and stuff like that. Maybe it's worth commenting on that in real life setting when you have something called like laminage. How about that pen? And then I have pen again. Okay. So you have like a bulk metal, which is like that. And here you have these two cylinders turning around. And basically, you have this bulk metal entering on this side. And basically, you have a, let's say, a thin sheet. This one is not so thin that enters at that side. Here you have some kind of von Mises material. And all of a sudden, this is like isotropic plasticity, which is generalization of this simple case. And here you have something called Hill criteria, and it turns out that it's like, different type of material, but yet it's the same material which was just squeezed by this lamination process to turn into thin sheet that I later on used in the producing, let's say, the body of the car or airplanes or whatever it is that you need the thin sheets to use for. So basically, one way is taking what people are doing. In von Mises' case, people are using something like if I'm plotting the deviatoric plane. So these are the principles of the stresses. See, this is sigma y, this is sigma 2, and this is sigma 3. This is the principle of my stress tensor. And then von Mises' criteria is actually a perfect circle in this deviatoric plane. It's not such a perfect, sorry about that. It should have been here in the center and stuff like that. So basically, this is the measure where I have my sigma y and so on that I start yielding. And then Hill criteria, people, instead of a circle, they're making ellipse, something like that. And they are typically measuring, yield stress in this direction, then yield stress in that direction, they raise that direction, and they consider some kind of ellipse instead of a circle. Well, this is only partially correct, because in fact, what really happens is that when you are squeezing this bulk of metal in the lamination process, what you're really doing, recall when you have elastoplastic with hardening, this is your epsilon, and this is your sigma. So you go until sigma y, with elastic process, and then basically after that, you go into hardening. And this is EK divided by EK. And then you download and you get your plastic deformation and stuff. So if you go in this direction, if I put this as the cut, and this will be like, in the plan. So in this direction, you basically kind of plastifying your material. So you really have lots of, you actually at this level of the stress. So your let's say your sigma y is some kind of let me put it like that, sigma threshold, like this is sigma t. And then in the lateral direction, you're not doing anything to your material. And so indeed you have your sigma y because and so all of a sudden, that becomes like that. But this is simply because in one direction material was hardened and the other direction it was not hardened. And this is definitely a much better description that you take into account what is the plastic deformation in this particular direction. So you have the epsilon plastic, and this happens in the lamination. So this is your at the time t for any value of x, and that's precisely what I had in mind. So basically, at that time when we started discussing this, there was a sadly famous case of washful, a crazy cow or disease. And there was a question that if you want to buy beef, you better buy beef which was produced in France, not in the United Kingdom where the beef was coming from. So I was joking, if they can have a beef says produced in France rather than in the United Kingdom, you can have a sheet metal which says produced by lamination process in this direction, and then you can have definition of these plastic deformation precisely defined and quantified. And then you build on top of that, because this was the initial condition for your sheet, and you can then orient this and rather much better than the Hill criteria, which is simply at that time used heavily. We were collaborating with my colleagues at UTC who were working for car manufacturing with lots of these things with the explicit method and stuff, and I tried to sell that, and basically it was always too complicated for them to do it. So basically you have kind of initial field for the plastic deformation hardening level, and this is one example where this could get into the business. And I would just start from the initial condition, then carry on my computation. But here, to make it simple, we keep it like there's no this initial condition at all. Then I will follow the path of the finite element solution scheme. In other words, I'll get my representation of the displacement field by using the finite element interpolation function NA, and I'll have to respect the imposed displacement at the boundary where the displacement is imposed. And for the virtual displacement, these are not functional time because we are freezing the time and taking the particular deformed configuration that correspond to a given level of applied loading. And basically, we are applying the weighting function of virtual displacement to be equal to 0 at the boundary where we impose displacement. Now, for the plasticity, there's a very nice book called Temam. Temam was this mathematician who worked with Jacques-Louis Lyons, who was like the professor in the domain of applied mathematics. and the book is called something like Mathematical Formulation of Plasticity, where he introduced the concept of bounding deformation. So bounding deformation, we'll talk about that when you go to the softening and stuff like that, is the fact that even if you have jumps and you have yield lines and whatever cracks and stuff like that, the dissipation of energy and stuff remain bounded, roughly like that. But we won't dwell on that before going to really softening. We'll just keep using our shape function that I normally used. Then I basically like a linear like that, one at node A and 0 at all the other nodes. So let's go back to the definition of the plasticity. So instead of strong form, we're going to be using the weak form, which says that the work of the internal forces, this is the virtual strain, dw dx, multiplied by sigma. So what has changed with respect to elasticity? Sigma is not only functional total strain, but also plastic strain hardening variable. And it's also a function not only x, but also t. External loading is also functional t, applied traction is functional t. And in order to compute the stress, we have to go through elaborate description of stresses either in the stress rate form or computing the evolution equation and making sure that evolution is constrained, that is phi is always -0, gamma is always positive and 0, and gamma dot phi is equal to 0. So basically, how we do the computation. First, we go this Galerkin approach. So we get definition of our displacement field. Once I have a displacement field, I can take the derivative, compute the total strain as a BA times dA. It's not written here, but we've done it before. Then I can take my virtual displacement, take the same shape functions. The only difference would be when I impose the displacement, I'll need extra description to take into account exposed displacement, but it's known value of displacement, so it doesn't change much. And here we'll be just eliminating all the displacements which are constrained because the value of this WA are equal to 0. So when I take this discretization and plug it back into the weak form here, I obtain so-called Galerkin equation, which says that the free nodes value of this virtual displacement multiplied by the residual should be equal to 0. And that amount saying for any arbitrary value of this free node displacement, which is 0, residual has to be equal to 0. And that amounts to saying that the internal force, which is d and dx, that is dA, multiplied by sigma, should be matching the external force for each and every of these situations. So this time around, we obtained, again, not a set of linear algebraic equations. In fact, these are heavily nonlinear because nonlinearity is hardening a sigma. And again, these are evolution equations. So we'll need a equation in time. So we'll need also the time integration scheme that we discussed for heat transfer. Namely, the time integration scheme comes from basically evaluating the time variation of these internal variables, plastic strain is P missing here, and then hardening variable. So basically, the idea is like at the end, when I go through that, I'll appeal to the finite element method. In other words, this is the set of the equation that I had to solve. These are global equations, go from 0 to L. Then we say, okay, let's go now to the finite element what we learned. And we can really recognize the advantage of numerical integration, not only for simplifying the constructing of the arrays that are needed for each family of the elements that are the same, but also for plasticity. You'll see that in a moment, in a sense that the information for the plastic strain and internal variables is only limited to a certain number of points. I don't need these fields everywhere. I need it only for particular points. So basically, the idea goes as follows. I take the whole domain omega, I split it into subdomains omega e, and then I integrate this over a particular subdomain one by one for the same, let's say, family of these elements. And this goes from -1 to 1 if I go to this truss bar. So I have a global point of view and I have a local point of view that is exactly the same as elasticity. So for example, typical element of truss bar with 2 nodes goes in the global point of view from xa to xa plus 1. Here it goes from xi1 to xi2, xi1 is always -1, xi2 is always +1. Then nodes here are a and a plus 1, depends on numbering. In the element point of view, if you have 2 node truss bar element, they're always 1 and 2. Then degrees of freedom are dA, dA plus 1. They are global. Here they are local. They're just done d1 and d2 again for the element. And then we'll come back again to the assembly and stuff like that. That won't change really the fact that we have plasticity. What will change is just that the internal force, the tangent stiffness, so on and so forth, will be affected by the rules that are typical of plasticity. All the rest, assembly and stuff, it's exactly the same like for the elastic case. So in the global point of view, the piece of displacement that I need for the piece of the of the domain, this interval typical of the element omega e is NA of x times dA plus NA plus 1 x of dA plus 1. and here would be N1D1 and N2D2, both of them carrying the index E. That means element point of view. So, of course, we have seen that this is done already with the not integrating analytically, but integrating numerically. So, for example, trust bar with 2 nodes, we said it's 1 point integration point is enough. So it comes down to taking the number of integration points equal to 1, and that happens to be abscissa, which is equal to the center of the element. So CL is equal to 0 and WL is equal to 2. And then basically that amounts to saying that I need a total strain in the center of the element. This can be computed from my interpolation for psi equal to 0. That's the same like in elasticity. And on top of that, I have to store the plastic deformation and hardening variable in the center of each element. So typically, these internal variables are computed only locally at a particular Gauss point of an element that we are interested in. The element which plastifies has to now have the possibility of storing in the database the plastic deformation hardening variable, and then you can carry on the computation you might need. How do you get these values? You get them from evolution equation. Namely, you have to solve the plastic deformation dot equal to gamma dot times d phi d sigma, which is sine of sigma, and xi dot equal to gamma dot. And this evolution has to be in agreement with the gamma dot being positive, phi being negative, and gamma dot times phi equal to 0. So recall that we had an evolution equation that are computed by the time integration schemes, and basically that while I have to do that, and maybe just one more, let's say, remark before we go to this explanation how you can actually compute it. With the numerical integration, the internal force comes down finally to computing the stress value at the center of the element, for which one you need the storage of the plastic strain and hardening variable at the center of the element. For each and every element, there's this particular storage. This is done locally, and the global strain is computed from the total displacement vector with the standard finite element interpolation. So there's like a global level for the total strain, there's local level for plastic strain and hardening variable. The same goes for the tangent elastoplastic stiffness. Recall that was like a B times BA times BB for any component KAB times the elastoplastic modulus. So elastoplastic modulus for hardening with the linear hardening is the one here. I go back to the picture. It's basically either E or EK divided by E plus K that you can obtain. So you have to know whether you are elastic, whether you are plastic, and in particular, it's incremental analysis. You're simply sticking this value into here. So again, to be able to know whether you're elastic or plastic, you have to have mastered the plastic deformation, hardening variable, and stuff like that. So it's very handy when you have a numerical integration, both internal force, which is here, and tangent stiffness are using the same number of integration points. External load doesn't have to do anything with the behavior, so you can take a different number of integration points and do this computation here very quickly. So maybe I can give you this result, and you can kind of play a little bit with that. So let me give you a little bit of exercise if you want. If you have if you have something like a truss bar element with let's say a T bar here, and you want to have some kind of a T bar going to 1.5 sigma y, and then minus 1.5 sigma y, you can obtain what that is. You can do this, I want you to have an epsilon sigma diagram for this case. And you can then take, instead of that one, you can take a B, distributed loading, and so say that B times L, the total load is also, so it's either T bar or it's a BL. And you can again produce this for this case and that case. So what will be the difference? The difference will be the stress field. So here, hopefully this will be constant and is equal to that one. Here will be linear because you basically start like that. So plasticity will not happen throughout the one, but only the part where you're kind of reaching beyond. And so the trick is how big is the mesh that you have to use. Can use 1, 2, 3, 4 elements, whatever you want. So try to a little bit to play to see a little bit how it goes. and hopefully this will kind of demystify. So first of all, what I then want to discuss is how to solve this problem. So typical story is that we came to the set of the differential equation. We have a basically going back to this one, you have your equilibrium equation. You have your equilibrium equation in the weak form, and then you have this evolution equation for the plastic strain and the hardening variable as we go along. So typical story is we now use time integration scheme with one step, because one step really simplifies the storage for the internal variable. If you had this multi-step solution method, that would be really a nightmare, because you would have to take bookkeeping, taking plastic strain from I don't know how many steps. So really one-step method, the one for the simplicity of handling the database kind of management for this type of case. So the goal is as follows. I know the state variables. These are the strain, total strain at x bar. X bar is typical the Gauss integration point obtained by interpolating from a global displacement field and taking partial derivative with respect to x. Then I have a plastic deformation which is stored, and I have a hardening variable which is stored. And I have my time step h taking me from Tn to Tn plus 1. So now this provides me the sigma n to be E times epsilon minus epsilon plastic. And I want to find this total strain, plastic strain hardening variable at n plus 1, such that basically that again I have my stress, and that phi should be negative or 0. In other words, this is the type of problem I'm solving. I'm having 3 fields: total strain, plastic strain, and hardening variable, and I'm having 3 equations. If you want to call for each and every element, you have an equation like that. So in order to plastify, you have this evolution equation of the plastic strain and hardening variable, and then equilibrium equation that concerns all the displacement. And that has to be done with respect to the so-called plastic and relative stress field, that in each and every element, the absolute value of sigma should not go beyond the value which is sigma y plus kxi. There's a kxi missing here, and so on and so forth. So basically, there are 2 choices. One is definitely explicit method. And in the book of Roger Owen and Ernie Hinton, written a long time ago, they were playing with this explicit type of plasticity computation. So let's recall this equation and see what we would do with the type of thing like that. So basically, you would have this on one side. Oops, pen. When I have epsilon plastic dot equal to gamma dot times sine of sigma. Oops, sine of sigma. Boop, not very nice. That doesn't matter. And then here I have xi dot equal to gamma dot. Here I had an equation which is a f internal minus f external function of time equal to 0. So for this equation, what I'll do is I take derivative with respect to time. This amounts to saying I have a df internal dd times d dot equal to f external dot So basically, this will be just the tangent stiffness, okay, elastoplastic. And from this one, I can write d dot is equal to a minus k elastoplastic inverse times f dot. So if I use the Euler explicit method, recall that was simply saying that epsilon plastic n plus 1 is equal to epsilon plastic n plus h, which is the time step, times gamma n dot. Often these two together are called gamma n without dot. times sine of sigma at time Tn. Sigma at time Tn, I know it's equal to E times epsilon n minus epsilon n plastic. Then psi of n plus 1 is equal to psi n plus gamma n. We call gamma n is h times gamma dot. And here I can say that dn plus 1 is equal to dn minus k elastoplastic minus 1 at time Tn multiplied by h times f external dot. And this is together, I can call it delta f external at n plus 1. So basically, the explicit scheme has big advantage because that's very easy to solve. I know that sigma n is equal to E times epsilon n minus epsilon n plastic. So I know the value epsilon n, I know the value epsilon plastic, so I can very easily obtain what is the value. I know then the sign, and I can compute my epsilon plastic without any problem. Then I can know Cn plus 1, also even gamma. I know whether it's elastic or plastic. If it's elastic is 0, if it's plastic, that's the value that I have. And here I can compute also this one to be, it's actually step of incremental analysis where the tangent stiffness is the one which is computed from the elastoplastic. So let's say Kn elastoplastic, this is what you can use in your computation, would be simply the, for this particular element E, would be integral over omega E. And here would be have a B, let's say this is A B component. So this will be like BA, this is dn dx. Then you'll be C elastoplastic at time Tn. So C elastoplastic at time Tn, it could be either E if you're elastic, it could be like EK divided by the sum of E and K. Oops, tap, E and K if you're elastoplastic. Up. And times BB, and this will be it. So basically, you can compute from this one dn plus 1 very easily. It's incremental analysis. And then from that one, you can compute epsilon plus 1. Now, when you compute all this, you can compute your sigma n plus 1 following the same recipes as epsilon n plus 1 minus epsilon n plus 1 plastic multiplied by Young's modulus. Then you can compute phi n plus 1. And then phi n plus 1 is basically the absolute value of sigma n plus 1 minus sigma y. It was minus q n plus 1, and this is plus k times psi n plus 1. This is k, and then psi n plus 1. So this is how I can compute the homework that I just gave you explicitly. Now, everything is nice, but the problem is now whether this phi is negative or 0. And can I be sure? Well, here, recall again, this is E times epsilon n plus 1. Minus epsilon plus 1 plastic. So basically, I have computed epsilon plus 1 plastic from this equation. Then I have computed the total strain from this equation. These two equations have nothing to do with one another. And then I plug this in here, and I compare this against the value, which is Cn plus 1 that I computed from this equation. Again, the third equation has to do nothing with the other two. So it was wonderful that I could use the explicit scheme because nothing stops me from computing anything I need. Less wonderful, I cannot be sure that this is less than or equal to 0. And basically, you recall there was a critical time step when I have explicit scheme to be equal to less or equal to 2 divided by lambda critical being the eigenvalue of this matrices. So this is related to this tangent stiffness matrix. But in the case of plasticity, it's not enough to worry only about that. You have to worry about the time step, which makes P negative or 0. So what we're advocating in the book of Owen and Hinton is basically reducing the time step. So you're sure that not only you have stability, but you also have this plastic admissibility of the stress, which becomes really nuisance because the more you go, you know, from one step to another, you have many, many different elements. So, you know, from one point to another, you are not sure whether you have your plastic admissibility or not. And so the explicit scheme turned out to be not so good enough, but if you have, let's say, explosive events or something like that, you can still try for that. One can though try with a compromise to have something like implicit on this one and explicit that one, which is kind of good, because when we had the job of after World Trade Center attack, verifying the security of some kind of nuclear installation for French army, and then we did a very complicated model of this, whatever, crashing the airplane and stuff like that. Basically, the idea is that we did this one explicitly because it was impact and frictional contact, and this one was done implicitly, so you can have a stress admissibility. But that's the compromise. If you really want to go safe and sound for everything, what you do, you go for the implicit scheme. So now we want to solve this set of equations, which is here, two evolution equations for each and every Gauss point where the element plastifies, and the set of equilibrium global equation implicitly. Now, the trick is as follows. These two equations are local equations. They just concern particular element which plastifies. That not necessarily means everywhere. Whereas this equation is global equation, and it's certainly much more costly to solve and to handle. So we do something called operator split. We don't solve these two equations simultaneously. Typically, we start with the solution of this type of equation, provide some kind of guess of the total strain field, and then we go into these evolution equations there. So if you, within incremental analysis, the first solution should be just first, let's say, incremental step that you get obtaining there. So this is then the case that you're handling. You're going, given that the guess of the best value for the global, let's say, variable like a total strain field at time n+1, iteration I. As I said, incremental analysis simplifies the value that you had previously. Let's say you say this is your best historical value and you fix it, you don't touch that anymore, then you're computing the evolution of these internal variables. So this comes to a local computation which concerns only one Gauss point of each element where the trust bar plastified. So not all the elements might be concerned, and certainly not everywhere, but just the Gauss points that you want to do. And of course, if there are many elements which are concerned, you can handle this computation simultaneously, because the way they plastify, again, given the total strain field, you can go and carry out this computation. So how does it go? First of all, I try to say I need to find the plastic strain and the hardening variable, which would allow me to compute my stress, given the total strain iterative value minus plastic strain, compute it that way. And I want to make sure that I'm plastically admissible. In other words, that phi is less or equal to 0, that gamma dot is positive or 0, and product between gamma dot and phi is equal to 0. So I take an implicit scheme, backward order. So basically, I'm computing from epsilon possibility equal to gamma dot times sine sigma, something like epsilon plastic n+1 equal to epsilon plastic n plus gamma n+1 times sine of sigma n+1, where gamma n+1 equal to h times gamma n+1 dot. And the same thing for the hardening, sine +1 is equal to n plus gamma n+1. There's no sign because it's simply 1. But the problem is here, I do not know the value of gamma. I do not know the value of sigma. So what do? I know that basically gamma could be either negative or 0, sorry, either positive or 0. So I start with the simple case. I start with a guess that computing this equation, I start that gamma now is equal to 0. That would imply that I'm undergoing elastic step. What that means is basically I'm either have been here at time Tn, and when I'm going to n+1, I never really left the elastic domain. Or the other scenario would be I was at time Tn here, and then I started unloading, so I went inside, and my n+1 froze the plastic deformation. That's precisely what I get, getting gamma n+1 equal to 0. These two drop, and basically it says that plastic strain at n+1, hardening variable n+1, is the same as the previous step at time Tn. Then this is still trial. That's why I called it trial. And basically, how would I know it's right or not? Well, I now compute my stress, sigma epsilon trial equal to E times epsilon n+1 at iteration I minus epsilon plastic trial, which is equal to epsilon plastic n. And then I take my phi n+1 trial, which is basically absolute value of this minus sigma y plus k times psi n, which is the tri-value of psi n. If this happens to be negative, that means I'm either here or there, I find this is the end of the story. I also know that my elastoplastic tangent modulus is equal to E because I'm either unloading or I'm loading in the elastic domain. How would I know if I'm wrong? Well, if I take phi n plus 1 and I find the positive value, which was the case I already alluded to in the explicit computation. Now, this time around, I know how to correct. I say, no, this cannot be possible. Phi n plus 1 trial cannot be positive. My guess of gamma n plus 1, 0 is wrong. Now I know that gamma n plus 1 is positive. I will compute it. An extra term to do computation is that I enforce phi n plus 1 to be equal to 0. So unknowns of this computation are now epsilon plastic, hardening variable, and my plastic multiplier gamma n plus 1. So I have three equations, three unknown, everything is perfect. So basically, either I can solve this simultaneously, or I try to exploit what I already had. This is the tri-value of phi. So it is easy to show when you meddle down with this equation. You can actually reduce this to a single equation, which says that gamma n plus 1 is phi n plus 1 trial. There should be trial here, sorry about that, divided by E plus K. And then you get your gamma plus 1. Once you have it, then you plug into these two updates and you get plastic deformation and hardening variable. This time around, well, this is not perfect picture because it should have been, you had time Tn, and then at n plus 1 trial should have been just a straight line. It should have been somewhere here. And then basically you are projected down to the yield surface with a fixed value of total deformation. This is illustration of this type of thing. If you want, I can well, doesn't matter. You can imagine, try to sketch it better as in terms of your homework when you're doing this homework, and you'll see if you can. Basically, the idea is like, this is sometimes called radar projection method because in 3D, as I said, the vectoric plane is something which is perpendicular to hydrostatic axis, and then you can have a circle and so on and so forth, and then you're coming down to the center. We'll talk about that in a second. So basically, the idea is really that with this one, you can have a implicit computation. You get the plastic admissibility of the stress field. Everything is perfect. You get either elastic step or you get your plastic step, and then you're ready to go back to the global step. In other words, you started this computation by saying, I know the best iterative guess for the total strain field. It might have been wrong. How would I know if it's wrong? Well, I go back and recompute my internal force. I recompute external force. I get my residual. If this residual is small compared to 0 beyond the tolerance, then my guess for the epsilon plus 1i was perfect. If it's not the case, I linearize again by keeping internal variables fixed, and I get the new iterative improvement with the Newton's method of the total displacement field, and I improve my epsilon plus 1 to a new value, epsilon plus 1, I plus 1, and I repeat the local step. So it's always like a global step, local step, global step over, and I can then advance. So goal of the global step is to get me the best approximation for the total strain field with displacement and all that stuff. And goal of the local step is to give me plastic admissibility of the computed stress. So this way is always like quite fine. And these two steps are ideally separated because the amount of computation is certainly not the same. In the global step, I have global equations. And in the local step, there's a bunch of the local equations that concern each and every Gauss point computed separately. So now if you go for a refinement of this plasticity model, you can have many type of different things. What I really wanted to just say that if you look into that, how we compute it, basically, the idea goes as follows. In many of these situations, people have been kind of introducing, here's the most well-known docs on plasticity. So in UK, there was Rodney Hill, wrote a very nice book in 1950s, and he kind of worked out plasticity of metals for that time. I started already with plasticity, J2 plasticity. Then Jean Mandel was before German, the professor at the École Polytechnique, so he wrote the influential book, Plasticité classique et viscoplasticité. And then my former colleague from École Normale Supérieure, who created this laboratory of mechanical technology, Jean Lemaitre, he wrote a very influential book on damage. It's called Mécanique des matériaux solides. Then one of my former professors in Berkeley, Jacob Lubner, he was actually writing a book when I was following his courses. And really with him, I learned this thing that you should not be doing. It was really very nice book on plasticity with lots of analytical solution stuff. He was not into numerics. But the idea is like, he was, I think, of Polish origin. He came to US later. studied at Columbia, then became professor in Berkeley, and was a really good professor, but he kept this European type of feature when he was kind of writing this equation on blackboards. It's analytical solution, sometimes you make mistake. Then he was giving handouts of this book while he was writing it. So we had a really wonderful support for our course. And I really had a very high opinion. But then he would make mistake. He would go red and yellow and stuff like that. And what the hell, really felt embarrassed. And I said, my God, there's no reason to feel embarrassed because this is really high level. And what if you find a mistake in the blackboard, you have almost glued to the blackboard, that's not the problem. Then I had another guy in mathematics called Alex Chorin. He also wrote many influential papers and books. He was doing mathematical physics type of course I had to follow. He was explaining the theory of Einstein with this random walk and Brownian motion and stuff like that. And I remember he was writing the full sentences on the blackboard, not only equations. So if you write everything, you could almost publish a book after his lectures. And basically, when he would make mistake, like everybody can make mistake, then he would say, oh, okay, well, here there's a mistake, but doesn't matter. Here's homework, you do this, you do that, and that, just go on. I said, there's the difference in mentality between US and Europe. There you get embarrassed because of a small mistake, but what the hell, better not to be. It's actually better when the lectures are not perfect. Anyways, but the idea is really what I tried to convey, compared to all these books, and then there's numerics in Simon Hughes. The idea is like, I tried to convey that contrary to this development, they study from the beginning 3D case, that actually what we are doing is very conducive to 1D case. So maybe I'll finish with that. If I now go to 3D case, and I want to generalize everything that I was talking about in 1D case to 3D case, what will change? Practically nothing. I will just have to use bold-faced letters. Namely, three main ingredients as follows. I want to take the message from this lecture today as follows. I have a total strain. I have to split for plasticity small deformation setting. When you have a small displacement gradient, every component is much, much smaller than one. As I said, 400 megapascal divided 200,000 Young's modules, that is 10 to the minus 3 times 2, which is really, really small. So for this case, the total strain can be split into elastic and plastic additively. So basically, if I go from 1D to 3D case, what happens that epsilon now is a tensor, second order tensor, which has 3 by 3 components, has 9 components. And I have to split each and every of those components into elastic and plastic. It means dilatation, shear, and so on and so forth. So different materials are sensitive to different type of situation. As I said, for example, plasticity of metals is most about shear because Tresca and Hormesis and stuff is about that. Then if you go to plasticity or like cohesive materials like concrete or something like that, it's mostly tension and things like that. So each and every component which is representing particular model deformation can be split into the elastic and plastic. That's the first ingredient. Ingredient number 2, I have to have a energy type of potential. So here, if I generalize something that we had for linear hardening, this will be like a total strain minus plastic strain tensor times the elasticity tensor, which is 3 by 3 by 3 by 3, multiply again total strain minus plasticity strain. But again, it's a scalar product. At the end, it's a scalar. I just have contribution from each and every different modes. And then here will be hardening. Again, it could be something like a vector type of thing, psi, multiplied by instead of hardening modules, could be like a matrix. And then again, stuff it. So then I have to have a yield criteria. First of all, here I can build my dissipation to happen to be, let's say, sigma dot epsilon plastic, and then hardening variable, which are minus d times xi dot. And then basically I have to have the particular criteria, which says, when do I start plasticity? So criteria has to be done in terms of the stress tensor and the hardening thermodynamic conjugate flux. After that, when I have defined this, so other than bold-faced letters, I have an additive split, I have a free energy, and I have a yield criteria. Nothing else changes. It's just in 1D. After that, I define my dissipation. Happens to be, if you neglect that these are bold-faced letters, very similar to what I had in linear hardening. This is sigma dot epsilon plastic dot, and then Q times psi dot. And then you maximize this given that you have a constraint over admissibility of the plastic strain, and you get your evolution equation for the plastic deformation, hardening variable, and your loading and loading condition. Obviously, you can no longer, if you have 3D, so easily come up with the rheological model, because how the hell you would put all these springs connecting to one another. But you don't need it. You can follow the procedure to establish valid for 1D case and simply push it to the 3D case. Then finally, you need let's say, plastic consistency condition. If you're yielding at time t, you have to do it at time t plus dt. which amounts to saying if I want to have plastic, phi dot should be equal to 0. So in 3D case, you can kind of unravel this condition even more refined. You can have a gamma dot equal to 0 when you have either elastic loading or unloading. In other words, if you are inside the elastic domain, this is representation of the elastic domain for von Mises. We'll study it next time. Basically, which is a circle. So inside, it means you're in the circle if this is the rhetoric plane, or you are entering again inside the circle if you have been plastic on this side. And then you have like a plastic loading. That means you're expanding the plastic domain if you have hardening, or here in this case, you have something called neutral loading. It's tangential. This is just detail and so on and so forth. And then basically done. Once you're done, you can recover your gamma dot. Here it is d phi d sigma dot c times epsilon dot divided by d phi d sigma dot c d phi d sigma plus d phi dq dot d phi dq. Again, this is scalar, so gamma dot is given scalar. And you get your stress rate constitutive equation that are basically either elasticity modulus times the total strain when gamma dot is equal to 0, or this is like a elastoplastic modulus times the total strain, which is a modification of your elasticity modulus times epsilon dot time when gamma dot is positive. And this is the kind of thing that you follow there. Now, all these things that you follow, these are like different type of details, and you'll see that all of a sudden there are many coefficients that pump into this type of thing. But really, there's nothing to worry about because it doesn't change the significance of what we're talking about. It's simply like a different interpretation with 2D or 3D, let's say, glasses as opposed to 1D glasses, but certainly more credible to what I was appealing to, like interpreting tests and so on and so forth. So maybe we'll stop here and let you ask any questions or comments if you have, and before we take it into